Hello students, welcome to the class of Control System 2. I am Priyanjali Mukherjee, Assistant Professor of Engineering Department of Narula Institute of Technology. Today our lecture is on the developing of state space model from the system. This video contains the defining a state space representation, consideration while selecting the state variables, developing state space model from mechanical translating system, developing the state space model from electrical system, the reference and the MCQs. So during the analysis and performance of the control system, which we have discussed in the earlier classes, was based on the transfer function model and the graphical approach. The graphical approaches may be the root locus, the Nyquist plot or the Bode plot. And those approaches are called the conventional approach. Now, due to the different disadvantages or limitations of the conventional approach, we have used the state space representation. The state space representation provides a more complete description of the control system. The transfer function approach is generally used. Some of the practical results of state space approach can most compactly and usefully presented in terms of the transfer function. So, this is the basic model of state space. We are already discussed with this. For the linear system, the state space model can be expressed by two equations. One is the state space equation or state equation and another is the output equation. So the state equation is x dot is equal to ax plus bu and y is equal to cx plus du. And this state model may be the multiple input, multiple output or the MIMO system. And in this, u is the input vector, y is the output vector and x is the state vector. So we can represent the x dot by the set of differential equations and the y, that is the output, with set of some algebraic equations. So we can determine the state variable model from these two equations, and also we can define the transfer function from that state variable model. And in this video we will discuss that how to determine the transfer function from the state variable model and its vice versa. So next is the consideration while selecting state variables. So during the selection of state variables, we have to keep in mind that we have to choose the minimum number of state variables to avoid the redundant number of state variables. If we select the larger number of state variables, it can causes the computational complexity, and due to that the controllability, observability or the both can be decreased. So always we will choose the minimum number of state variables. So to find out the state model from different representations of the system, there are basically the linear time invariant control system can be represented in three ways. One is the physical variable form, next is the phase variable form, and last is the canonical variable form. So among these three, today we will discuss the physical variable form and its state space representation. So generally, first we need to know what is the physical variable form. So first we need to describe the control system by formulating the equations that describe the dynamics of the control system. And then we will select the state variables, and one method is to choose the physical variables as the state variables that are associated with the energy. The number of state variables may be equal to the number of energy storing elements in the control system. So if we consider the electrical and mechanical system, so in case of mechanical system, the potential energy and the kinetic energy of a mass are the functions of position and velocity of the mass. So therefore, the position, displacement and the velocity can be chosen as the state variables. So here we will develop the state space model from the mechanical translating system. So first we will state the assumptions, and then we will establish the internal coordinate system. We will identify and isolate the discrete system elements such as the spring, dampers and masses. Then we will find out the minimum number of variables which is required to identify, and then we will draw the free body diagram for each element. Then we will write the equations relating to loading to deformation in the elements, and finally we will apply the Newton's second law. So take one example for this. So here this is the example of developing the state space model from the mechanical translating system, and this is a mass spring damper system, and this mass is connected to this damper and the spring K. And due to the application of the force, the mass has been displaced in this direction, and the displacement is represented by yt. So we will write down the equation for the mass. If we draw the free body diagram, then we can see that the force is acting in the opposite of these forces, Fb, Fk and Fm. So Fm becomes the m d square by dt square, and as the y is displacement, so this d square by dt square is representing the acceleration. Next is plus b dy dt. B is the damping coefficient and dy dt is the velocity of this system, plus the ky, where k represents the spring constant and y is the displacement of the given system, and f of t is the applied force. So after writing this equation, we can write that d square y dt square, as it is the highest power, so we have kept this in the left hand side, and d square y dt square is equal to minus b by m dy dt minus k by m and minus f by m. So next we need to find out the state variables, or we will assign the state variables. So here we can take that x1 is equal to x of t, and if x1 equal to x of t, so x1 dot that is equal to x dot, that becomes the x2t, and similarly x2 dot t becomes minus b by m x1 minus b by m x2 plus 1 by m into f of t. So now we are getting these two equations, dx1 dt or x1 dot is equal to x2, and the second equation dx2 dt equal to or x2 dot equal to minus k by m x1 minus b by m x2 plus 1 by m into f of t. Similarly, the output can be written as x1 of t. So, from these two equations, we can write down the state equation x dot equal to a into xt plus b into ut. So, x1 dot becomes x2. So, the coefficient of x2 becomes 1 and the remaining coefficients will be 0. So, this matrix first row will be 0, 1 because this 0 is the coefficient of the x1 and this 1 is the coefficient of x2. Similarly, this 0 is the coefficient of f of t. So we can rewrite this equation in the matrix form like this: x1 dot is equal to 0, 1, x1, x2 and plus 0, 1 by n ft. And similarly, for the next one, x2 dot, we can write the equation of x2 dot in the form of matrix, and the coefficient of x1 becomes minus k by m, the coefficient of x2 becomes minus b by m, and the coefficient of f of t becomes 1 by m. So this one becomes the state equation, which is the form of x dot is equal to axt plus but. And the second equation is the output equation. And the output equation, we can write y is equal to only x1 into t, because there will be no input term. That is, ut term will not present in the y equation. So that's why y is equal to 1, 0, x1, x2. You can write here plus 0 into u. That means the d is actually 0. So the form of this output equation, y is equal to cx plus du basically, but you can remove the d because the d becomes 0 over here. So in most of the cases, the d is actually the input output coupling matrix, and DUT indicates the direct coupling of the input to the output. And the direct coupling of the input to the output is very rare in the control system. So that's why the D becomes 0. So the output equation can also be written as yt is equal to c into xt. And these two equations, you know, that together called the dynamic equations of the system or the state model of the system. Next is the developing of the state space model from the electrical systems. So electrical system is also in the physical variable form, and during the electrical system we will consider the RLC network with capacitor and inductors, which are the energy storing elements. So the rate of change of the current in the inductor and the rate of change of the voltage across the capacitor can be chosen as state variables. Also, the current in the inductor or the voltage through the capacitor, that is can be taken as the state variable. And if we choose another physical system such as the chemical system, then we can choose the rate of change of temperature or the rate of change of pressure or the rate of change of flow as the state variables. And then similarly we will convert the system equation into the first order differential equations, and then we will derive the state model of the linear time invariant system by the state equation and the output equation. So here one current source is present, and the current source is giving the current IA, and one inductor, one capacitor is in parallel combination, and a series resistance and inductor is connected in another branch. So here we will choose the inductor currents, that is IL1 and IL2, and the voltage across the capacitor as the state variable, and voltage across the capacitor is given as small e1 and voltage across the inductor given as small e2. So IL1, IL2 and E1 can be taken as the state variable of the given system. So next we can use the KCL in each node. So first we will consider the inductor L2. So if we consider the inductor L2, then the drop across this inductor becomes same that of the capacitor, that is E1. So you can write the equation in this way: L2 dIL2 dt is equal to E1, and from this equation we can write dIL2 dt is equal to E1 divided by L2. And similarly, in case of the capacitor, you can write the equation d1 by dt is equal to 1 by C1 into the currents, that is IA minus IL2 minus IL1, because at this node IA is incoming and IL2 and IL1 is the outgoing current. And if we apply the voltage, consider the voltage at the L1 inductor, then we can write E2 is equal to L1 dIL1 dt, or E2 is equal to this E1 minus R into LI1, or this dIL1 dt becomes 1 by L1 into E1 minus R1L. So we have found out already these three equations. One is dIL2 dt, which is the first derivative of IL2, that means IL2 is the state variable, and dE1 dt, where the E1 is taken as the state variable, and third one is dIL1 dt, where the IL1 is taken as the state variable. So if we rewrite these equations in the form of the state equation, that is general form, x dot equal to ax plus bu and y is equal to cx plus du, we can find out that this A matrix or the system matrix becomes 0, which is the coefficient of IL2, the 1 by L2, which is the coefficient of E1, and the coefficient of IL1 becomes 0. Similarly, the next term is minus 1 by C1, which is the dE1 dt, that is E1 dot, and the coefficient of the IL2 is minus 1 by C1, and the coefficient of E1 becomes 0 and the coefficient of IL1 becomes minus 1 by C1. Similarly, for the third one, that is IL1 dot, the coefficients can be written as, for the first one, that is for IL2 the coefficient is 0, and for ILE1 the coefficient is 1 by L1, and for the IL1 the coefficient is minus R divided by L1. So the system matrix can be written in this form, and in the same manner we can find out the matrix B, which is also known as the input coupling matrix, and it will be a order of n cross 1, and n is 3 over here because there are two inductors and one capacitor, so there will be 3 number of state variables, and as there will be 3 number of state variable, the system matrix will be n cross n, that is 3 by 3 matrix, and B matrix is 3 by 1 matrix, or this is a column matrix, and the C matrix, which is also known as the output coupling matrix, that is a row matrix of 1 by n, and here n is equal to 3, so it is a 1 by 3 row matrix. And in the same way, the D has been determined as the 0, which is actually the input output coupling matrix. So in this way we can develop the state space model from the electrical system. And different models of the linear time invariant control system are the phase variable form and the canonical variable form. The state space representation in the canonical form again further classified as the controllable canonical form, the observable canonical form, the diagonal canonical form, and the Jordan canonical form. And we will discuss all these state model from different representations in the next videos. So these are my references. So I hope after this video lecture, you have a clear idea about today's topic. Now we will go through some question answer session in context of this video lecture. So you are requested to go through it gradually and solve the problems by your own. All the answers are attached at the end of each question.